To begin Unit 1 on stoichiometry, the first thing we're going to do is review how to do mental math. And mental math really entails having to do your mathematics quickly without a calculator. And the reason why we're doing this is because the multiple choice portion of the AP exam involves no calculator, and that would be also expected of you as well when we do take an MCQ section of our tests. So let's go ahead and review a little bit. I'll do one or two problems and you'll just go ahead and work through the rest of the problem sets. Okay. If you look at this problem right here, I see the exponent. It's a negative number, so I'm going to move my decimal over to the left to make it a smaller number. Negative means it's going to be less than 1 probably. So if I move this decimal right here between the 7 and the 4 over 3 spaces to the left, I would yield the following number. And that is 0.0074. So that's my answer for that one. Now, on the other hand, you're going to notice here the exponent, it's greater than, or it's positive, so you're going to move the decimal place over to the right instead of the left to make it a larger number. And in doing so, you will get the following number, 656. So go ahead and work through these problems and make sure that you can you understand it. You can always enter into your calculator to check your answers for these. We're not going to give you a key for that. Now we go to the next set. Put these numbers in scientific notation. Again, I look at the number and I see that if it's less than 1, I know my exponents are going to be negative. And I always, according to this scientific notation format right here on this side, I always want to have my numerical value between 1 and 10. So n is always between 1 and 10. It can equal 1, but it cannot equal 10. So in order for me to put my number in scientific notation, I would make my number 5.7. And to give to the between that decimal point right here that I have to the decimal point right here to the between the 5 and the 7 is 3 spaces. So this would be times 10 to the negative 3. I'll do another one with a big number instead. So in this case, in B, you've got 2.74, and I'm maintaining sig figs. Notice in letter A, there were 2 sig figs, and notice when I put my scientific notated number, I'm still maintaining 2 sig figs here. Likewise, in this number right here, there's 3 sig figs, so my answer is going to be in 3 sig figs as well. So times 10 to the power of 7. So, and you'll notice it's 7 powers from this decimal, which is invisible at the end, all the way to here is 7 placements of 10. So 7 powers, 10 to the 7th power. Again, go ahead and work through the rest of the problems so that you have the practice you need. Do as much as you can to make sure you understand how to put these numbers into standard notation or scientific notation. Now we get to the hard part. The hard part is actually in the calculation. So when you're calculating these numbers, you have to sometimes move it out of standard or scientific notation and get it into standard notation so that you can add those numbers together placing them correctly in the decimal place that they are aligned to. So I might be working the problems out on the side here. So if you take these two numbers right here, you'll notice and this is addition, so I'm going to have to take these two numbers and take it out of the scientific notated number or scientific notation. And I need to erase this. And when I do that, I will get 7,400. And then likewise on the next number, add a scientific notation into standard notation. I get 1200. And upon doing that, I can then add those two numbers knowing their decimal places. And so I get 8,600. So 8,600 is my final answer, and it's asking us to write it in scientific notation, so it's 8.6 times 10 to the third power. Let's move on to the next problem. In the next problem, letter B, you're multiplying two numbers. So you're multiplying these two scientific notated number. And when you multiply, and if you've got the like bases like this 10 here and this 10 here, what you do to the exponents is you just add the exponents. Whereas if you were dividing these two numbers, like this problem right here, you'll subtract the top exponent or the top integer of that base to from minus the exponent for the second base. So let's go ahead and do that for B, letter B. So multiplying these two numbers, you get, let's see, 3.0 times 10 to the 10th power. Okay, so 2 times 1.5 is 3, and then the exponent, you just add the exponents together. 5 plus 5, 5 plus 5 right here, and that will give you the exponent of 10. Now when you're subtracting, it's completely, it's subtraction of the exponents rather than addition. So to do this problem, it would be 3 divided by 1 is just 3.0, maintaining sig figs, times 10 to the negative 2. 2 minus 5 is negative 3. So go ahead and work through those problems and make sure you're practicing. You truly have to practice to make sure you're doing this math without having a calculator at hand. So putting numbers in scientific notation and solving problems without a calculator can be very taxing, but you do your best to try to work through it. So going back to this tip that we saw earlier, it says put everything in scientific notation or fractions so that the math could be easier. So I don't know if you realize this, but 0.125 is really 1/8. So you can actually, and how I looked at it is, I kind of looked at it in a very long way. I took it into what it means, which is 100. This is 0.125, which is 125 thousandths. So that's what this, because the 5 is in the thousandths place, right? The tenths, hundredths, thousandths. So if I put this into fraction form and reduce it down, you'll notice that it becomes this really nice fraction of 1/8. Okay? So it's 1/8 as a fraction. So what is 1/8 of 8/10? So it really is dividing it by 8, and so it's a tenth. So in letter B, I see that this point for 0.500 can be a fraction, a nice fraction. It's 1/2. So what's 1/2 of 0.6 or 0.125? It's like taking half of 106 or 125, which ends up being 62.5. But if I move the decimal place over 3 spaces, it's 0.0625. So many times, if you put things in fractions, I think it will help with solving the problem with more ease, if anything. We're getting into SI conversions. SI stands for Système International, and it's the international system that we use for measurements in the scientific community, including the metric system. So let's go ahead and go into the metric system. Metric system, the part that we will use the most is from kilo to milli. So King Henry died by drinking chocolate milk. And all the metric system is the movement of powers of 10, either multiplying by powers of 10 or dividing by powers of 10. So if you look at our first answer, when we work through it, or our first problem, it says how many centimeters are in 1 meter? So you're going from meters to centis. So it's 1 to powers of 10, 2 powers of 10 moving over to the right. So when we do that, when we move 2 powers of 10 to the right, we see that it is 100 centimeters. I'm going to jump down to number 3 because that movement is a little bit different directionally. So you're going from 520 centimeters to meters. So centi to meters. So the base unit. So you're moving it 1, 2, 2 powers of 10 to the left, which means you're dividing it by 100 rather than multiplying by 100 in number 1. So dividing it by 100, you get 5.20 centimeters. So once again, review and practice all of this mental math, all the problems that we have not done, you haven't done with me, so that you can get really good at it. Now reduce and solve. So when we've got fractions multiplying by fractions, it's smart to cross cancel where you can cross cancel common multiples, and then multiply from there. Okay. Let's see. So reducing. There's a couple of things you can do. If you spot it, the quicker you can spot it, the better you're off. So I'm going to spot. I see that I can take the 20 right here. There's 20 right here, and there's 200 right here. So I can cross the 20 out, and I'm left with 10 here. I can cross the 7 out. Oh, I can cross the 10 out. And then I'm left with just 6. So when it comes to fractions, multiplying by fractions, best to cross cancel where you can cross cancel in the end. So this is in B. We see on the bottom that we have 300, so 30 times 10 is 300, and this is 150, so it's like half, right? So we can cross cancel the 150 and say that this bottom is a 2. But then we see a 2 here, so we can cross that out. We see a 4, that becomes 1, and that becomes 2. So we're left with 3 halves. Okay. So you can move on, work through those problems. Solving, when you're getting down to algebraic math without a calculator, it's best to, once again, just practice your shortcuts that you can do. I like to move decimals where you can move decimals. Where I see powers of 10, I'm moving them around. So there's 10 times 1,000 is 10,000. So that's 4 zeros, 4 powers of 10. So what I do is I take, with 4 powers of 10, I just move this number right here 4 times over to the right. So really, this is now not 0.08. 4 spaces over to the right now gives you 800. 2, 4, yeah, 800. And so now when you solve for V here, so it's just dividing this by 5 to solve for V. And to divide it by 5, you just see that it is, for every 100, it is, how many 5? 25s, right? So 8 times 25, 20 is 160 in the end. Let's go to B. So here we have 15. There's a multiple right here. of 5. So I would kind of leave that as a fraction so that you can cross multiply or cross cancel factors out. So that would, if you divide both sides by 10, you'll get P equaling, and then I would then go 1, 2 here because you can factor out, pull out 5 from both top and bottom factors, and so you're left with 3 halves. In letter C, you see that you can reduce the fraction on the left side. You actually can reduce this to 5. So 25 divided by 5 is 5. So that's exactly what I'm going to do. Where you can reduce, you would do that. And so when you multiply, cross multiply, so you get P equals 10. And once again, I would do the same for D, where I see that I can reduce this fraction to something simpler. I would do that, and that way I can then cross multiply where I need to cross multiply and solve for my unknown variable. Okay, hopefully this helps you through learning how to do mental math without a calculator, so you should refrain from using a calculator through this whole section. I'd like you to take some time to read the learning objectives. This will be our little starting part of our introduction to a whole unit. Usually there are learning objectives to make sure you understand what you're trying to do objective-wise through each of the parts of this unit. So please do that. And then I wanted to go back and reintroduce this mapping that stoichiometry is always about mole ratioing in a chemical reaction, a balanced chemical reaction, and how you go from mass to moles depending on what you're dealing with, whether it's gases, whether it's density, which allows you to go to moles if you have the volume, which Avogadro's particles, knowing that Avogadro's number, which is 6.022 times 10 to the 23rd particles, can lead to moles because 1 mole, that would represent 1 mole. And then whether it's solution concentration, so molarity, molality, mole percent, mass percent or volume percent or mole fraction. So all of these lead to moles quite easily as long as we can eliminate parts of these ratios if it's a ratio in the end, like these, okay? Please make sure you study this mapping as a way to review what we've learned so far and apply it to this unit again. We're going to start off with percent composition, empirical, and molecular formulas. You should be very familiar with this. If not, you might want to go to some YouTube videos to recall and review. But I'm going to go over it as well here to make sure you also recall. Now, empirical mass is the mass of the empirical formula. Empirical formula is the simplest whole number ratio. Molecular are multiples of that whole number ratio, and then molecular mass would be the mass of any molecular formula, including it could be empirical formula as well. So when you're given something like this and you have to fill out what the formula is, if the molecular mass, right here, is equal to the empirical mass, you can only deduce that the formula is the same as well. So it must be the empirical formula. And yes, the molecular formula is, in fact, one example of a molecular formula is a multiple of 1, which is the empirical formula. Now, in the next set of problems, you'll notice that you're given the molecular formula as well as the empirical and the empirical mass. And you're asked to find what must be the molecular mass without having to just without looking at the periodic table and finding the molar mass of this whole formula. What you do is you compare the formulas and you notice that it's twice. The molecular formula is twice that of the empirical. Thus, the mass of the molecular mass is going to be twice that of the empirical. So twice this is going to be 32.02. Now we go to the next one. In the next one, we'll see that the molecular mass is 132 and the empirical mass is 44. And of course, they gave us the empirical formula. So it must be comparing these two. In other words, take 132.06 and divide it by 44.02. You'll see that it is 3 times. So it's 3 times the formula or the mass, thus it's 3 times the formula. So what's 3 times each of these moles of atoms? It looks like it's N2O3. Now we get to a scenario where you're given molecular formula and molecular mass, or you might have discerned the molecular mass from the molecular formula from the periodic table. And then you are asked to find the empirical. Now the empirical is always the lowest whole number ratio, so reduce 6 to 12 to 6 reduces down to a 1 to 2 to 1 ratio. And upon reducing that, you'll see that it's a sixth of that, so you take 1/6 of 180.2, and that would be 30. In other words, divide it by 6. We go to the next problem. You are asked to find the mass percent of oxygen in phosphoric acid. And the key is to understand and recall how to name compounds like phosphoric acid. And I've always taught you that when you name phosphoric acid, the ic comes from the ate. So this comes from phosphate. And we've had enough review on polyatomic ions and knowing what they are as of now, or as of this point. And so an acid means it's got a hydrogen ion. So if you put a hydrogen ion with a common ion or a polyatomic ion that has a 3- charge, the formula to neutralize those charges is H3PO4. And so our goal in this problem is to find out what the mass percent of oxygen in phosphoric acid. So we're going to need the molar mass of this whole substance. With your periodic table, you find out that the molar mass is 97.99 gigagrams. And of course, since there's 4 moles of oxygen, you take 4 moles times oxygen's molar mass, which is 16 in the end. And when you do that, you will then divide it and multiply by 100 to get the mass percent of oxygen in phosphoric acid. Now we go to a different problem. In this problem, you're given the mass percent of each of the elements in this unknown compound that's called NutraSweet. It is the synthetic sweetener. Now you're asked to calculate the empirical formula. And in doing so, I like to assume there's 100 grams. Why 100 grams? Because percentages are based off of 100. And so when you assume 100 grams, you can take those masses directly from those percentages. So this really means 57.14 grams of carbon. This really means 6.16 grams of hydrogen. And then so on and so forth between the oxygen and nitrogen. Now, since I have all the grams, I need to convert them to moles. And upon doing that, using the molar mass of each of those elements, molar mass of carbon being 12.02, hydrogen 1.006 or 08, or 1.01 to be more precise with your old periodic table. I'll actually post the new one, the AP periodic table, out for you all, okay? Soon. It actually reports the mass of hydrogen as 1.008. And then oxygen 16 grams, nitrogen 14.01. This is all obtained from their molar masses of those elements on the periodic table. So we calculate the moles of each of these elements and then we insert it into the formula. And we notice that this formula makes no sense whatsoever. We've always seen whole numbers. So then we divide it by the lowest molar value, which is 0.68. And then we get these values. Now, we're close enough to whole numbers, but not quite. So we have to find ways to multiply this to try to get a whole number. And because 0.5 is 1/2, it's a fraction of 1/2, to get rid of the fraction is to multiply everything by 2. And upon doing that, multiplying everything by 2, I get this empirical formula for NutraSweet. Now, I do want to go over patterns for when you have fractions. So I really want to make sure you see all the possible fractions that you'll come across when it comes to these formulas here, trying to find the empirical formula or molecular formula from the percent composition. So if you ever have a fraction of 1/2 or 0.25 or 0.33, 0.66 or 0.75, these fractions equal, or these decimals equal these fractions. And so what you want to do is multiply by the denominator to try to get rid of those fractions and make them whole numbers. And so I'm going to multiply this formula right here by 2. Multiply this formula by 4. This formula by 3. By 3 and then by 4. And in doing so, I will get these low whole number ratios that are most meaningfully whole numbers. And that's the key, is trying to get these numbers to be whole numbers and the lowest ratio you can possibly have. So those are your two problems that I would like to show you for percent composition. Now it's your turn to do these problems. There's the MCQs. They're located at the end of this file, of this document, and they're labeled by MCQ. And this is the FRQ I'd like you to go through. Please understand that answer keys are there for your checking purposes. They're not for you to just write down as your final answer. To do a problem is to show all your work, and completely all your work, step by step. So please make sure you take your time to show that work as you go through these problems. Hopefully I gave you some room to do the FRQ. If not, try to squeeze it in on the side of your notes somewhere. Please work through these problems and make sure that you are getting these answers. Now, with any word problem, it is very important to really take some time to build this skill. So please make sure you are really totally determined to figure out how to solve these problems on your own. The more you do on your own, the better you will be at it. So again, these are the answer keys. We will go over some of these questions in class. So now we're going to discuss sources of lab error. And you've been doing this all year last year, where we always had an error analysis in the lab report. And the discussion of the error analysis is oftentimes what would happen if something else were to get in the way of that or the results. And so we're going to go over this. This problem was really meant to be not an FRQ, but really an example problem set, because I like to give you an example problem set for every single topic in this unit. So let's go ahead and start with A. It says calculate the number of moles of iron in iron 3 oxide produced. And so if you look at the data, reading it carefully to yourself, or I'll read it out loud as well. A student is given a sample of powdered iron powder that contains an inert impurity. The student uses a procedure to oxidize the iron in a sample of iron 3 oxide solid. The student collects the sample data during the experiment. So obviously the word oxidize means that it reacted with oxygen in the end to form iron 3 oxide. So it's a synthesis reaction. Now we're going to calculate the moles of iron in iron 3 oxide. And you'll notice that every 1 mole of iron 3 oxide has 2 moles of iron in it. So depending on how many moles this turns out to be, we are converting it to moles. We will then ratio it knowing that every 2 moles of iron are in 1 mole of iron 3 oxide. So let's go ahead and begin. Let's start off with our given, which is 7.531 grams of iron 3 oxide. And once again, I always label what I'm doing so that I know and track what substance I'm trying to find. So 1 mole of iron 3 oxide has a mass, so the molar mass is 159.7 grams of iron 3 oxide. And then you mole ratio that, knowing that 1 mole of iron 3 oxide has 2 moles of iron in it, then you can calculate the moles of iron, which ends up, if you calculate it, and please always do the mathematics. I know the answer is right here in front of us, but never assume this calculation will yield this answer. So please make sure you work through the mathematics, always. So working through the mathematics, I get 0.09431 moles of iron. And then the next one says calculate the percent by mass of iron in the original sample of powdered iron with the inert impurity. So if we can find the mass of the iron right here, we know that all this iron is from this iron that's in the sample, the mixture of sample with the inert impurities. So there's other impurities in there. So we're going to calculate mass of that iron. So we're going to convert our moles of iron into mass. And upon doing that, using the molar mass of iron, and please print out that periodic table and the equation sheet that's located in the reference sheet folder in Schoolology. And I will get from that calculation 5.2675, and there's much more digits, but I'm just going to I'm going to get a little bit more than the sig figs that's required. And then I'm going to take that and divide it by the total mass, so that's the mass of iron, divided by the total mass of the impure iron sample. So, and then times it by 100 to get my percentage. And upon doing that, I get a percentage of 78.34% iron in that sample. Now we're going to look at a different, this is essentially where the error analysis question is. So if the oxidation of iron in the original sample was incomplete so that some of the 7.531 grams of product was iron 2 oxide instead of iron 3 oxide solid, would the calculated mass percent of iron in the original sample be higher, lower, or the same as the actual mass of iron in the sample? Justify your answer. So what you have to do is compare the iron 2 oxide from the iron 3 oxide. And in comparing those two, I'll notice that the iron 2 oxide has a mass percent of iron that is, so I'm going to do just purely the grams of iron in the grams of iron 3 oxide, or iron 2 oxide. And I'm going to get the percent by mass of the iron that's in there. And when I do that, there's only 1 mole of iron, and the iron 3 or iron 2 oxide is 71, the molar mass is 71.85. I get a percent of iron that is 77.73% iron. And then I would do the same also for the iron 3 oxide. So for iron 3 oxide, I would divide the moles, there's 2 moles of it, of iron. So I'm getting the percent of iron in iron 3 oxide. And why I'm doing this is I want to know how much iron, the mass percent of iron in one versus the other product. And so I get 69.94%. Now, since the iron 2 oxide had more iron in it mass-wise, that means that the original sample would have a lower amount of iron in the end. So because there's more here, there's a higher percent of iron in the iron 2 oxide than the iron 3 oxide, you will see that there's a lower amount of iron in the original mixture, which is right here. So that's the logic behind why you would expect a lower amount. So I'm going to circle that as my answer in the end, a lower amount than the actual percent of iron in the mixture. Now it's your turn to go ahead and work through this FRQ, FRQ4, and FRQ5, which is the next page. And so please make sure not only you're working through it and thinking through the logic of what would happen if this error occurred in this situation, and then go ahead and see what the effect of that error would do. Would it cause a higher or lower yield in the end for that hydrate problem? And there's 6 different possible errors. Okay. Now we go into stoich. This is where we do stoichiometry with limiting reactants, and we're going to model as well. So we're going to see some particles as we model the microscopic scale modeling of that problem. So let's go ahead and look at example 3. In example 3, it says right here, if you have 10 grams of hydrogen reacting with 20 grams of oxygen, how much water in grams will be made and how much of the excess reaction will be left over? How much of the excess reactant will be left over is better worded. So here's the answer. However, let's go ahead and ice this. If you recall, when we do stoichiometry, we like to ice it as a way to know the initial, the change, and the end, what happens at the end. And you start off with a balance equation, and you want to work in moles. So whatever you have in grams, you start off initially as your gram units converted to moles. So here's my conversion to moles, grams to moles. Grams to moles here's as well. And of course you can do that on the side if you want to make sure you show your work that you can do that calculation. But it's a simple for hydrogen. It's just a simple 10 grams divided by its molar mass, which is 2.0. I think hydrogen is 1.008, so 0.16 now, based on the periodic table. And so this is your gram to mole conversion, grams per mole. And so that will give you your moles, which is 4.96 moles. Likewise, you would take the grams of the oxygen, so this is O2, and oxygen's molar mass, 20 grams. Oxygen's molar mass is 32 grams per mole, and so when you divide that, you will get the moles, the amount in moles, which is 0.625 moles. We place it all into the ice table under the initial, and then you figure out who the limiting reactant is. Now recall, to find the limiting reactant is to divide it by the mole coefficients, and the one that with the lesser amount of moles is going to be the limiting reactant. And so what's this number divided by 1 versus this number divided by 2? This one will give you 2 point something, this one will give you 0.6. So you right off the bat you can tell that this is the limiting reactant right here, oxygen. So that's why you subtract the limiting reactant, and of course twice that amount because of the coefficients. Twice that amount will be how much hydrogen reacts against oxygen, and then of course twice is how much you make of the products. And then you find out that in the end your limiting reactant will be 0, and then you'll have some of your excess left over as well as your products. And when you convert that into grams, so this is a mole to gram conversion, you'll notice these are the masses, and this is truly what the answer is for both the excess as well as the product form, which is water. Now, when you look at the law of conservation of mass, all of stoichiometry overall is always going to be guided by the law of conservation of mass. So the mass of both the product and the excess gives you 30 when you add them together. And notice when you add the reactants, it's 30 as well. So mass is conserved. The mass that you started off, you end up as well. So the mass has to equal in the reactants as well as the products in the end. Now we go to percent yield. And percent yield is just an equation, simple equation of taking the experimental and the theoretical. Now the theoretical amount of water was 22.5 grams. That's how much you theoretically should form given these amounts here of the reactants. So 22.5 grams is how much you theoretically should form. Now in the problem itself, it says that you actually form only 20 grams. So the experimental is 20 grams. And when you do the percent yield, you'll notice an 88.9%. Your aim is always 100% yield. But because of error in your experimental part aspect, and we did a lab last year where we formed iron, it was iron 3 carbonate, and we saw this orange powder that we filtered out. And we often saw that our yield was less than or sometimes greater than 100, depending on if the solid or the precipitate that formed was a hydrate itself, because it would probably cling to more water from the air. Anyways, I am going to draw a lot of information from last year so that you can recall. But oftentimes the discrepancy in this yield is due to some kind of error, some kind of lab error of some sort. Okay? So now we're going to model limiting reactant problems. And so you're going to see particulate drawings. The first thing you want to do when it comes to these problems is to make sure you write out the balance chemical reaction. So I'm going to start off by writing out the two reactants, which is hydrogen gas plus oxygen gas will yield water vapor. And I'm going to balance this equation and put the mole coefficients in front of each reactant or product. So it looks like I'm going to need 2 here, and it's 1 here. Oh, sorry, it's 2 here and 1 here. So I'm going to erase that just so I can be clear on the mole ratio. Okay, so it's a 2 to 1 to 2 ratio of hydrogen to oxygen to water vapor. So the first example number 5, we count particles. That's all we're doing, and we're seeing how much they should react and eliminate each other as they react. Okay, so let's start off with hydrogen, and it looks like we have 1, 2, 3, 4, 5, 6 particles of hydrogen, 4 particles of oxygen, and 6 particles of water. So we're going to fill that in. But let's make sure we understand why there's 6 particles of water. So oftentimes you're not given the amount of water. You have to kind of predict how much water that would form. So if you have, like we said earlier, 6 here and 4 here. And of course, the stoichiometry is a 2 to 1 ratio here. You take this, divide it by 2, take this, divide it by 1, and you get 2 values. The one with the lower value will be the limiting reactant, and it looks like the limiting reactant is going to be hydrogen. Let's go ahead and write Lr for hydrogen. Now, with hydrogen being the limiting reactant, and there's 6 moles of hydrogen, we know that the ratio between hydrogen and the product, so the product will depend on the limiting reactant, and the ratioing is a 2 to 2. That means for every 6 moles we have of hydrogen is going to be 6 moles of water vapor, and that's why we produce, in the end, 6 moles of water vapor. Now let's get into our excess. We know our excess is oxygen. We know that all our limiting reactant is going to react to only react some of our oxygen. So how much of our oxygen will react? Well, if 6 moles of hydrogen will react, half of that is going to be how much of the oxygen will react. So notice the 2 to 1 ratio. So half of that is actually going to be 3 moles. So if you subtract 3 moles of oxygen, you're going to get 1 mole left. And so there's going to be 1 mole of oxygen left over. And the limiting reactant, as we stated earlier, is hydrogen. And the excess reactant is oxygen. Just reiterating that over there. And let's go ahead and look at the next problem. In the next problem, you see 2 moles of hydrogen. So you can kind of get used to this diagram. We've been diagramming, we've been doing these microscopic or microscale illustrations for some time already. So now we have 3 moles of oxygen. The limiting reactant in this case is going to be, so 3 divided by 1 versus 2 divided by 2. The one with the lesser amount is going to be our limiting reactant, and it looks like hydrogen is going to be our limiting reactant. So that means oxygen is our excess. So hydrogen is going to be our limiting reactant, oxygen is our excess, and the amount that we're forming, once again, is always ratioing the products to that of the limiting reactant. So the product here and the limiting reactant right here is a 2-to-2 ratio. So 2 to 2, which means since we're forming or reacting 2 moles, we're going to form 2 moles as a result. The leftover is going to be oxygen. And so take a look at the oxygen. If 2 moles of hydrogen reacts, that means only 1 mole of oxygen reacts, which leaves us with how much left over? Well, we're going to subtract that 1 mole that's going to react, and we're left with 2 moles. So 2 moles of oxygen left over. Let's go ahead and look at the next problem, example 7. In example 7, we read there's 0.365 grams of an unknown contains silver, so it actually has other stuff other than silver. If an excess amount of chloride ion is added to a solution of the unknown and 0.206 grams of silver chloride are produced, because silver and chloride will be forming a precipitate. It's insoluble. What is the mass of silver in the unknown? What percent of the unknown consists of silver? So the first thing you want to do is figure out the actual substance that's forming with all that silver. So this is going to be containing all of the silver chloride that you see here. So I'm going to convert my grams of silver into moles of silver chloride, and then I'm going to figure out how many moles of silver are in that silver chloride, and then I'm going to convert it to grams. So this is how many grams I see of the silver that's in the silver chloride, which should be the same amount of the silver that is in this mass right here. So then I sit there and go, okay, if this is the mass of silver that I know for sure is in that unknown compound, to find the percent of that percent of silver in that unknown compound is to divide it by its total, which is 0.365 grams of the unknown. And so then you multiply by 100 and you will get your percent by mass of silver in the unknown. Your turn. So go ahead and work through these FRQs. These FRQs will have many different varieties and styles and different ways of being asked. So you really, once again, got to practice how to do these problems on your own. So go ahead and work through this one on your own, including the MCQs that are asked of you. Okay, so this is your practice time. This page is also your practice time, so go ahead and complete the FRQ 7, and then, of course, continue on to practice FRQ 8. Go ahead and work through FRQ number 9, FRQ 10, 11, and then one thing I want to talk about, this is, by the way, the end of this unit. Past this unit, you will see this multiple choice scale, which you probably have taken a look at, but this is the star system that I have is a system that I use to understand whether it's a very easy, medium, or very hard problem. And the percent of students who've received a correct answer on that, it kind of helps you to see perspective-wise how you do against that. And then the percent of MCQs on the exam. So topic-wise, what you will see more frequently on the exam as far as level of difficulties. Past this point, you will see problems, an AP problem set, which you will do and complete. And then you will also see some optional problems. So anything that says opt means it's an optional problem. The more you do, the better you are. The more efficient as well as accurate you'll be at figuring out how to solve these problems. So I highly recommend doing as much as you want or can to until you get enough practice for your own good.